Okay, so now I'm recording, and for fracture interference to happen, the stress added by the presence of the fracture is going to have to be higher than what do you think? In order to have a reversal of stress, that the minimum principal stress is not the minimum principal stress anymore, what do you think it should happen? And let's just to be clear that these are the initial stresses. So you go to a place and the initial stresses are these. But now you place a fracture, and now you are forcing sand to be into this fracture, and therefore you have an additional stress. So
S3 plus sigma, delta sigma for S3, that be your non-initial?
exactly. The non-initial in the proximity of the fracture is going to be the additional stress is going to be actually the net pressure, equivalent net pressure or closure stress in the fracture plus the initial stress. We're not going to go through the solution of this, but there is an equation and a solution for that equation that is called the Sneddon's solution, that tell you what that delta sigma is as you go further away from the fracture. And that delta sigma is going to be proportional to the net pressure in the fracture, and that makes sense because the higher the net pressure in the fracture, the higher the additional stress that you're going to have in here. It is proportional to the height of the fracture, and it is inversely proportional to, let's say this is x, distance from the fracture. It is inversely proportional to the distance. So this is not an equal, this is just a proportionality symbol. But so the idea here is that if this additional stress surpasses what was the initial stress anisotropy, then at some point, very likely closer to the fracture, if the initial net pressure or fracture closure stress is higher than this difference of stresses, then you have a stress reversal right next to the fracture. The minimum principal stress is not anymore in this direction, but it is in that direction. And as you go further away from the fracture, the influence decreases, and there is going to be a point at which you come back to a location in which the fracture or the minimum principal stress comes back to the direction in which it was originally. It's not anymore in this direction, but it is in this direction. So this is what is called in industry as stress shadow. Basically, it's the additional stress which is caused by placing a fracture. And the issue with this is that if you place a fracture close enough to another fracture so that the following fracture feels the presence of the other fracture, the fracture is going not to propagate as a planar fracture just in one direction, because remember, it always propagates in this direction because the minimum principal stress is always like this. But if now the principal stress direction starts to change directions, this fracture is going to start to bend. And if you force another fracture to propagate next to this one, and notice that this one is closer than the other one. This stage or this perforation is closer to well, the distance is the same, but if you had a fracture that starts in this direction, now this location is closer to this one than this one was to that one. So the fracture interference is going to increase every time more, and you may have, even in some cases, some of these fractures to run into the other fracture, and that's going to kind of defeat your purpose of having the fractures to grow in a planar fashion so that they reach to the maximum surface area as possible. Maybe the next fracture is going now to grow planar again, but now you have caused, in some cases like this, the fracture to go in a direction that you didn't want. So if you had, for example, a piece of rock somewhere over here, now it's not as well drained as it would be if you had a fracture to go in the expected direction in which you wanted it to be. In some cases, this fracture interference, let me exaggerate this a little bit. Let's put this one like too close here. You can have the fracture even to start propagating directly into the other fracture, because in this case the minimum principal stress is in this direction. So I wrote here current S3, which is not the original principal stress. So in order to avoid this, you need to know what is the minimum distance at which you want to put these fractures. And again, that's going to depend on the net pressure in the fracture, the fracture height, and very important, this is going to be the distance between fractures. It's going to be proportional to, again, the net pressure, fracture height, and it's going to be inversely proportional to the minimum principal stress, the difference between the intermediate stress and the minimum principal stress. And I think I'm forgetting something here. Can you think about anything that might be missing over there? So net pressure, fracture height, and difference in stress. Good question. It's not directly in there, but this net pressure, we know that it's proportional to the width of the fracture and is proportional to the Young modulus. So if the rock is stiffer, then it's going to require a higher net pressure for the same width to be propped. No, I think that's it. Yes.
So I'm just trying to understand. So because of the first frac, you're saying the direction of S3 will change. So
Yes.
why is the first frac still up and down, right? Because wouldn't you then assume that S3 is constantly to the west?
So
Like what happens when your S3 changes for the first frac?
for the first fracture, it didn't completely reverse,
Okay.
but it just here it bent a little bit like this. That's why the fracture is growing like that. So S3 is changing
And it changes because of
because of the stress added by this fracture. So when it starts growing, it will start to change. And sometimes it goes in this direction, then when you have this shape, it might go in the other direction. So that's not straightforward to say, but it will depend on the fracture height and also on the fracture length. Just as a simplification, that length between the fracture is going to depend on all these variables. It depends also on the fracture height.
And then in your little, in the Sneddon's graph thing,
Yes.
where is the X?
X starts at the beginning here
Okay.
of the fracture, and it goes in this direction.
Same direction as in the top one?
Yes,
Okay, good.
like here. I'm moving, with X, I'm moving from here to there. And the difference, the added stress decreases as you move away. So you could say, well, I'm just going to place the fractures a lot far away so they do not interact with each other, right? But what's the problem with that? If you place the fractures too far away, you're kind of wasting also that space. So you want to optimize that length so you do not have this fracture interaction, but also you maximize the number of fractures in the well. So you had a question, Mr. Go.
Why did you write delta sigma is, and then you have the arrow S2 minus S3? What does that mean?
What I mean is that what you have to evaluate is what is the change of stress with respect to the difference between the intermediate stress and the minimum principal stress. This is what is called differential stress. In places where you have small differential stress, then this fracture curving and interaction, it becomes very important because you add just a little bit of additional stress and you start to cause all these problems. But if initially you have a large differential stress, and if your, let me write this down. If your equivalent net pressure is smaller than the differential stress, probably you will have no problems of fracture interference. Because even if you go very close, the stress is not going to switch. S3 is not going to switch directions. The problem is when your net pressure is higher than this differential in situ stress. In that case, you may get fracture interference because now you may reverse the state of stress, reverse what it was minimum principal stress. For example, if minimum principal stress was originally east-west, by placing a fracture near the fracture, you will cause the minimum principal stress now to be in direction north-south.
So like the S2 and S3 flip?
Yes, exactly. They can flip due to the presence of a new fracture. Yes?
Can you write like an expression for S3 and S2 without like the initial thing? Could you say that S3 is equal to SH min plus or minus the delta sigma? Or would that constantly be changing?
So that will depend on that value.
Okay.
And actually, S2 is also going to change. Let's take a look to make this clearer. I have the figures here, but I don't have yet the writing, which I plan to finish this week and will upload, I don't know, hopefully tomorrow, about this part. But the figures are these. So this is a fracture, this is the fracture height, and the stress in direction X perpendicular to the fracture is this one, and it changes as you go further away from the fracture, but you also have a change in stress YY, which will be the intermediate principal stress. So those two change as a function of distance, and you have to find the point at which that difference does not make the original principal stresses to flip directions. So one solution to avoid this problem is to put fractures too far away from each other. But there is a smarter solution for this. You have a question, Mr. Nolasco?
Wait, so you said the stresses would flip. So with those two lines in the graph, would they flip that one, right?
Well, these are the additional stress that you add in direction X and direction Y. That will be, X will be the minimum principal stress and Y will be the intermediate stress. So if you change the original stresses, because S3 has a higher change than S2, you may cause a flip on S2 and S3. Okay, so, and well, since we're here we have some actual examples of simulations in which if you put fractures too far away, they grow relatively planar, but if you put them too close, they start to interact with each other and the fracture is not planar anymore. Alright, so as I was saying, one solution would be to place the fractures a lot further from each other, so you don't have these interference problems, but there is a smarter solution for this. And actually, it will involve, let me give you a hint, usually it involves more than one wellbore. So now we're adding one more variable to the problem. Before we had a drilling path, and out of that drilling path, this is the top view. Out of that drilling path, we have a horizontal wellbore, but in order to minimize the intrusion in the surface of facilities and everything, and also it's more economic, you can have a stepped out of the wellbore and have a wellbore that goes parallel to the previous one, and so now you can have multiple wellbores from the same drilling path. And now one more variable for design is going to be the distance or the spacing between the wellbores. Okay. So, any idea how you could do to avoid what you could do to avoid fracture interference if you have multiple wellbores? We're going to start here. Well, let's start. Let's say we're going to have a fracture here. It's going to be number 1. What can you do next in order to avoid fracture? Which one? Which wellbore would you fracture? The third one? Okay. So let's say we do one over here. Very likely that one will not be affected by the other one. And let's call that 1 prime. What do you do next? Which wellbore do you fracture? Number 2, and where? Right here? If you were to fracture right here, and very likely you will run into the other wellbore, and that's what is called a fracture hit. And sometimes you don't want to do that because you're just going to have your fracture to run into another fracture which is probably already propped. So you don't want to do that. Okay, but notice that if we fracture number 2 and we want to place that fracture relatively close, we have stresses that have been created by placing these 2 already. So instead of going directly into fracturing 2, what you can do is you can create 2 more fractures relatively far from each other, so they do not interfere. And after you even out the stresses from both sides, you can place a fracture in here. And in theory, and if the stresses are more or less the same from both sides, it should grow relatively planar. And this is what is called the zipper fracturing. And then it will continue the same way. So here then you will have then 4 and 5 and so on.
So can you explain what's the point of doing the 4 and then you have to go in the middle? Is that just like creating the stress regime inside so that it goes straight? Is that what's going on?
What is the point of 3 or 4?
What is the point of doing 4 and then 4 prime and then 5, which is to the right of 4?
Well, but it's the same as before. So you do 1 and you do 1 prime. They are not in the same position, so they are not going to affect each other.
Okay.
Then you put 2 and 2 prime, which are relatively far away,
Okay.
so they are not going to interfere with each other. And then once you create 1 and 2, 1 and 2 are adding stresses in this direction, which kind of cancel with each other, and so do 1 prime and 2 prime. So this one, instead of just having force from one side, it's going to have those stresses balanced from the 2 sides, and in theory should grow planar, because the additional stress that you put, even if they switch the stress when you just place 1, when you place 2, you cannot even out that. So the problem in the homework is a problem that involves zipper fracturing with 3 wells. And here I'm just making a schematic of 3 wells on the same horizon. But remember that sometimes if the fracture, if the pay is high enough, you could even put wellbores like one here, another here, another here, another there, in order to cover a little bit better the entire pay zone. So here, I mean, with this is depth. Okay. I'm not going to make schematics of the fractures, but because that's going to be a mess. But I hope that you can see this, extend this in 3 dimensions.
Would you zipper fracture that? This?
You could do zipper fracturing with this one too. Yeah. So all of these are horizontal wellbores. Probably we can add a little bit of 3D here. So these wellbores go in this direction, and these ones will be lower in that direction. Probably that 3D didn't help much, right? Anyways, okay. There is even a smarter solution for this, for avoiding the interference between fractures. And it's not that you're avoiding the interference, but you are not worried about anymore, or you try to for that fracture interference to develop, but so that it doesn't bother you. If you notice in the previous examples, we kind of forced the fractures to grow in a particular region. So we had some perforations at this location, then we have a plug, and you force the fracture to grow in here. You plug the next one, you do the perforations, and you force the fracture to grow into this particular location too. And a smarter solution is to not to force the fractures to grow wherever you want, but just to let them grow wherever the fractures want. And instead of having one perforation closely spaced in between two stages, now you have, in a single stage, you have multiple perforations. So here you put several perforation clusters. So each of these is a perforation cluster. This is a horizontal wellbore, and this one is a plug. So every time you move in each stage, you plug these two, pressurize this region, and you just let fractures to grow more or less wherever they want. If the perforation clusters are too close, sometimes you may get the fractures will try to grow in from all perforations, but if this one has an easier start, probably this one will grow longer than this other one, and if this one creates a fracture interference in this one, it may cause this one not to grow, and this one will grow, this one will not grow, and probably this one will grow too, and this one may not grow. But now you're not just betting all your fluids and proppant in one single perforation, but you're putting several clusters, so you let the fractures to grow wherever they can. And of course, you don't want to do lots of perforations because probably also that's not going to be the best solution. But you want to put enough perforations at a design distance between the perforations so that more or less, ideally you will want to grow fractures from all your clusters, but most time that doesn't happen.
Is this sufficient at all?
It is better than just forcing a fracture to grow in a single stage, because I think for a long time some of these stress shadow effects were kind of like overestimated. So people were placing fractures too far from each other. But with this design, you put less constraints on this. You just put multiple perforations, which are relatively cheap compared to a full-grown fracture, and you just let fractures to grow wherever they can. You have a question? Yeah.
So in the second one that you said it wouldn't propagate for some reason, can you explain why that would be?
Because if you have a longer fracture, when it grows, it will create the same thing that we saw before, an additional stress that is going to make it harder for this fracture to grow. So if this one grows first, longer than this one will exert more stress on that one and will inhibit the propagation of this one. Probably this one to grow under this additional stress is going to need a higher net pressure to grow. But remember that you are pumping all these stages at the same time. So the net pressure in all of these, at least at the wellbore, is more or less the same.
Really?
There's going to be a gradient. Okay? There's going to be a gradient.
So your first one would tend to grow the most.
The first one will tend to, if we imagine that we're pumping this direction, the first one will tend to grow a little bit more than the other ones because it has a higher pressure than these ones. But now this becomes a very complex problem because you have that slightly different net pressure. Also, there is proppant screening the proppant is richer at the beginning, and then when it gets into some of the fractures, it gets more diluted to the end. So it gets a very complicated, complex problem. But at the same time, it's like, well, you don't care that much about it. It's just that the fractures, they just grow and adjust on their own.
Could you discuss the cost versus efficiency with this one versus plug and perf, one that we talked about last time, of plugging each one and then doing each cluster separately? Like, is this cheaper than doing that?
This is not cheaper,
Okay.
but you have more fractures.
Got it.
And eventually you're gonna have a higher net present value because you can produce more. You had a question? No? But this is what is done today, okay? This is what is done today, and I like to call these ones, this type of fracture propagation is kind of the survival of the fittest, right? Because the fracture that can grow grows, and the one that cannot, it doesn't. Okay, so I'd like to share with you some numbers just to keep in mind about typical fracturing completion in the Permian. Today, okay? This is what is done today. Can you tell me, if you also did internships related to this, what's the typical length of a lateral? How much? 2,500 feet? 75? Well, yes, close to that. Oh. Okay, so let me fix this quickly. The typical length of a lateral today in the Permian, it's about 10,000 feet or more. Okay, how many miles is that? Yes, almost 2 miles. So 2 miles of the lateral going down in a horizontal direction. Okay, let's see if that solves the problem. A typical completion job in the Permian also has about 40 stages. So 40 stages of those with multiple clusters, and all right, there you go. And each stage has about 4 to 15 clusters. All right. Cluster per stage. You can do the math here about what is the spacing between stage. I think I did it between, if you divide this by that, it gives you like 250. And in each of those, you have 4 to 15 clusters. And data analysis shows that only about 60% of the clusters actually get open. 40% of those as we saw before, because there may be fractures close to each other, they never get a fracture in it. Each cluster has about 6 perforations per foot, and these are at 60 degrees from each other. So that means that, let's see if I can, this is going to be a real challenge. I have a perforation here. The next one, it goes like in helicoidal way. The next one is going to be here at 60 degrees from the other one. The next one is going to be here, and so on. You have about, in order to create these fractures, you have to inject 2 barrels per minute per perforation. And if you multiply the number of perforations times the number of clusters, that usually gives you an average value of about 100 barrels per minute for injection. And also, that's just injection rate. This results in about 2,500 gallons of fracturing fluid per linear foot of horizontal wellbore. So if you have a 10,000 feet wellbore, you multiply that times this number of gallons, and that's how many gallons of fracturing fluid you need. It's a lot. And last, usually in these completion jobs, you put about 2,000 pounds of proppant also per linear foot of wellbore. Let's do an exercise. We have 5 minutes. Tell me how many pounds, according to these numbers, especially these two. Tell me how many pounds of proppant go into every gallon of fracturing fluid, according to these numbers. I'll give extra points to whoever answers this question. How much? 0.8? Very well. Not too difficult, right? You require less than 5 minutes. Okay. Maybe, I don't know. I heard just one people first. Okay, so it kind of makes sense, right? So about a pound of proppant for every gallon of fracturing fluid. Okay, last thing for today. Do you inject the proppant at the very beginning or not?
No.
No? What if no, what do you do?
You put the pad.
You put a fracturing pad, right? If this is the injection rate in here, let me do this with colors. You ramp up the injection rate of the fracturing fluid. At the beginning, everything is fracturing fluid, but then you have a path in which you do not inject any proppant. And why that? Let's try to explain why you do that. Why? I can't hear. And what would happen if you inject some proppant at the same time? You will plug the entire well, or you could also sometimes interfere with the propagation of the fracture. Some people believe that you can, and actually the drilling people, they suggest that you can plug the tip of the fracture with, if you have particulate material in it. I'm not such a fond theory of that, but I believe that particulate material could interfere with fracture propagation. So at the beginning, you just open the fracture, and after that, you inject proppant by scaling proppant concentration to the desired value. There are some modern techniques that even suggest that you do not inject proppant constantly, but you inject that in slugs. So inject some proppant and then fluid, proppant, fluid, and in that way you kind of create, instead of a fully propped fracture with proppant everywhere in it. Remember that proppant is also something that you have to pay for. You prop the fracture with more like a heterogeneous distribution of proppant that at the end of the day is probably about the same as having the proppant of the fracture fully propped. So this has nothing to do with this one. This is for slug injection of proppant. Do you know about any alternative for proppant? You got a question, Mr. Moore.
Question regarding the slug theory. Do you risk closing the fracture between the slugs of the proppant, or does it remain open?
No, because you keep the total always the same. It's just that instead of ramping up the proppant, just inject some proppant, then nothing, then proppant, then nothing. Do you know any alternatives to proppant?
You can use a burner efficiency.
Okay, but you still need proppant, right? In some formations, you can also use acids to etch the fracture surface, and that kind of also helps the fracture conductivity after the fracture closes. All right, guys, I'll see you on Friday.